So it turns out that we can do something called transfer learning, where we take what's been learned by our models on ImageNet and we transfer it to different data sets. And the intuition is sort of, ImageNet is on a broad amount of categories. So we saw that we can have tandem bicycles. We saw that we can have African chameleons. So if it can learn some useful features to distinguish between those, if you have data sets that are, say, of plants or of people or of similar categories that are in ImageNet, then odds are that ImageNet has learned a useful representation that you can then leverage. So what we do in transfer learning is we simply chop the head off of our trained convolutional neural network. So we keep all the convolutional layers, and we kind of throw out the fully connected layers. And we replace them with our own. So what does this look like? We take our trained CNN on ImageNet. And again, ImageNet is available for everyone. ImageNet is an open source data set. You can even download models that were already trained on ImageNet, so you don't have to spend the days that it might take to train on ImageNet. And you then chop off the last few layers and replace them with your own layers. So layers that you initialize at random with k classes, based on however many classes you might have on your data set. And you take your new data and you start training again. And you keep this trained CNN frozen, and then you hope that your last layers will actually be able to generalize well on your data set. And it turns out that this works pretty well in practice. And more often than not, people typically choose to start with ImageNet as their starting point whenever they're building any kind of architecture. And this method works particularly well if the domain of your data set is similar to ImageNet. So again, if you're doing cars, people, cats, dogs, this will work particularly well. If you're trying to transfer learn from ImageNet based on spectrogram data, that might be a little bit harder just because the features that were learned from ImageNet weren't necessarily trained on spectrogram data. Another little point is you don't necessarily have to only freeze these layers. It's also possible to retrain the convolutional layers based on pre-trained weights, and this can also work well depending on how you do it. And this will also be impacted by the different choices that you make in terms of the model that you choose, the hyperparameters that you choose. So you might want to be careful when selecting the learning rate. For example, if you're training from a pre-trained CNN, because you don't want your weights to change too dramatically right from the start. You want to kind of help the network preserve what it's already learned to begin with. So again, this is what we see a lot in practice. A lot of models will use a backbone CNN. And what this backbone CNN means is that it's a network that was pre-trained on ImageNet, and then we use it for different tasks in any kind of different pipeline that we might have. So we consider this as a kind of feature extractor. So we take ImageNet pre-trained we take a CNN pre-trained on ImageNet, so it could be VGG, it could be ResNet. You take some kind of model that worked well, and then you use the feature extraction of your model to then go train a different neural network pipeline. And then you might have a very different task. So you might not even want to do classification. You might want to do a completely different task. But you know that the features that ImageNet has learned are very rich, and you might use those features in your pipeline. So in many ways, it serves as a generic feature extractor. So here's an example of this, but this kind of goes the other way around. So Facebook, well, Yann Lequin in particular, and I really recommend following him on Twitter, by the way. He always releases these different models and data sets that they work on. So they did something really, really interesting. They compiled a giant data set. So you can imagine that Facebook has not millions of images, but billions of images, right? ImageNet is on the scale of a couple million. Facebook has images on the scale of a couple billion. Now, they couldn't crowdsource and label a couple billion images, but what they did instead was very clever, right? People sort of inherently label their own images with hashtags. So what they did is they took these billion images, and they took the 17,000 most popular hashtags that were found on these images. And what they did was it was a kind of ImageNet on a much larger scale. So they took a giant model, and they had it predict the hashtags based on these images. And so this is really interesting. Again, I recommend you go read this post. So if they would have trained this on a single machine, they estimate it would have taken them more than a year to complete the model training. And so what they had to do was actually distribute this across 336 GPUs. And using 336 GPUs, it still took quote unquote, just a few weeks of training time. So you can imagine the complexity of this network. And then what they did is the exact same concept of fine-tuning, but instead of fine-tuning on a different data set, they fine-tuned on ImageNet. And of course, they completely crushed the top one accuracy on ImageNet. Now, I don't know if this would have been a valid submission to ILS VRC because they used transfer learning in this case, but this is just to show you how useful transfer learning can be for different tasks.